The name of this video is Sphere V from E. So for the first time, we attempt to find the electrostatic potential V from the knowledge of the electrostatic field E. Note that this is not the standard procedure. Typically, you want to do the other way around. That is, you want to find a simpler scalar function such as V, and from that find E. However, it's a good exercise to learn how to go from E to V as well. So let us consider the case of a hard sphere with a constant volumetric charge density ρ. So the sphere looks as follows. This is the center of the sphere. The radius is, as always, capital R. And we do the typical sketch where this is the R-axis. And in red, we have the E-axis. We already know the solution to this problem, as we encountered it already in the past. This is the origin, 0 here. So in particular, we know this point here, the electrostatic field takes a value here, which is simply ρ over 3 epsilon naught times R. Right at this point. It goes linearly from 0 to this point. And outside, it follows according to Coulomb's law. So it's R squared, and it's a continuous function in this case. So this function is actually C naught, because we go from something to nothing. It's not nothing, something on a surface, and nothing is from something in a volume to nothing, and so it's a C naught, even though the derivatives, of course, are not C naught, so you cannot use case 2. However, it is C naught, the electrostatic field. All right, so let us summarize what is actually the electrostatic field mathematically now, to give a full mathematical expression for this quantity. So the electrostatic field E depends only on R because of the symmetries of this problem. Inside is linear, and it goes as ρ divided by 3 times epsilon naught R UR. This is the field for R from 0 all the way to capital R. Note that we can already, because we know that it's continuous, include capital R in this case. Whereas outside it goes as ρ divided by 3 times epsilon naught times R cube, capital R cube, divided by small r square, Coulomb's law, UR. And this is for R contained between capital R included all the way to plus infinite. And once again, we can include capital R here because it's a continuous function, as we know right here. All right, so this is our electrostatic field, which is continuous. Now we want to use the definition of potential, that is E is equal to minus the gradient of V to find V. Okay, so in this case, we know that the only variable is small r, therefore we can write this as minus, instead of the partial derivative, simply the total derivative, because again, is only one variable of B, V is only function of small r, divided by the r. This is the procedure we want to follow to find the result, okay? And so basically what we want to do, we already encountered a similar problem before, we want to write dv, let's remember this minus sign here, as a function of r, has to be equal to this minus sign, we need to remember. So obviously, in this case, we need to remember also that there is a UR component here, which we can cancel out because this E also is only directed according to UR. So we can forget about the fact that there is this UR, so we can cancel it and we can only look at the scalars, okay? So dVr, therefore, is going to be equal to E, the component itself without vector, with a minus sign, so it's minus E, and again the minus is because I bring it to the other side here, times dr, okay? And then I want to integrate both these quantities between some limits of integration. And these are the limits of integration which we need to choose. Obviously here, the limits will concern b, whereas here it's just r, okay? And so that's the art of solving this problem, which is what we are about to do here. In fact, the first solution that we want to find is for the region outside the shell, the sphere. So we are in this region here. So the first part of the problem which we want to solve is for each point r in the region capital R included, all the way to plus infinite. So we are here, in this region here, okay? Okay, that's the first region we want to study. Okay, so in this region, as it turns out, we can very simply write down this equation, okay, this integral equation, as follows. So we want to integrate dVr from what value? From v at capital R, that's my starting point, all the way to any point v at small r. This quantity has to be equal to minus the integral between capital R and small r, and note that in the limiting case, small r can go to plus infinite, because it can go all the way to infinite, capital R to plus infinite, of minus, let's already substitute our knowledge of the component of E in what region? In this region here. So it's rho over 3 epsilon naught. Okay, we are in this region, capital R cube divided by small r square. We already got rid of the UR, as we have done here. We're only looking at the components at this point. And this quantity has to be integrated with dr. Okay, let's remember the minus sign. In particular, if we consider the minus sign together with the 1 over r squared function here, this integral simply gives us, on the left-hand side, v at small r minus v at capital R, which is our additive general constant, generic constant. This has to be equal to rho over 3 epsilon naught times r cube, which we should not forget. The integral of minus 1 over r squared is 1 over r between r, small r, so 1 over small r, minus 1 over capital R. Where I remind you that here we simply computed this integral, which is 1 over r, and this has to be computed between capital R and small r, therefore giving this result. But the minus sign is already built in here. Okay, this kind of makes sense because we have a 1 over r dependence, and we know that a Coulombian type potential outside is what we expect. It has to go as 1 over r. So that's a good sanity check, okay? What we don't know is this quantity V of r. This is our question mark. So first of all, let's rewrite this expression as follows. V of small r, which is actually what we intend to find, is equal to rho divided by 3 epsilon naught times r cube times 1 over small r minus 1 over capital R. We bring this to the other side, to the right hand side, therefore obtaining plus V at capital R. Once again, this is our arbitrary constant, which we want to compute. Now, if we impose normal conditions at infinity, or simply put normal conditions, then what we expect here, what we need to compute, is the limit for small r that goes to plus infinite of V of small r. This is a simple calculation. 1 over small r at infinite gives us 0. So we simply obtain minus rho divided by 3 epsilon naught times r cube, okay, times 1 over r. So this cancels, and here we obtain r squared, plus V of capital R. This has to be equal to 0, normal conditions at infinity. Therefore, our arbitrary additive constant V of capital R, it's nothing but rho divided by 3 epsilon naught times r squared, capital R squared. Okay? So this is a quantity which we want to store because we're going to need it in the second part of the problem. Okay, so we want to remember this quantity here. And finally, with using that constant, so with normal conditions at infinity, when we plug this back in here, plus rho over 3 epsilon naught capital R squared minus rho over 3 epsilon naught capital R squared, they cancel out, and so eventually, with normal conditions at infinity, the electrostatic potential outside the sphere, V of small r, is given by rho over 3 epsilon naught times, so this all goes away, r cubed divided by r. Capital R cube divided by small r, which makes a lot of sense because it's similar to this quantity here, but instead of having over r squared, which is Coulomb's law for the electrostatic field, for the potential we just get 1 over r, a type of potential. So this is the solution for V of r in this region of space. Now, what we want to do next, we want to study the region of space from 0 to capital R. All right, so now we need to investigate the other region of space, which is for each small r within the shell, that is for r between 0 and capital R. Okay, so in this case, we want to use again this type of equation. And so we're going to have the integral between, we are going from 0, so in this case for V, going from small r to all the way capital R. Okay. This is of dV of r, exactly like here. So the only thing we need to pick here is the limits of integration. And similarly here, we're going to have the integral, let's remember the minus sign here, of rho over 3 epsilon naught. Now we are in this region here of space, so rho over 3 epsilon naught. It's linear with r, ur is already gone, dr. And limits of integration, obviously, from small r, which eventually can go to 0 plus, to capital R. Okay, so this is the integral we want to compute. Now, if we look at this quantity here, R, we know that the integral of this quantity is going to be 1/2 r squared, okay, which has to be computed between small r and capital R. All right, let's remember this minus sign. So here we obtain, in this case, V a capital R minus, so there is another minus sign to remember. In this case, V of small r, this is the quantity we want to find. This has to be equal to minus rho divided by 3 epsilon naught times 1/2, so it becomes eventually 6 epsilon naught, r square computed at capital R square minus small r square, with a minus sign, but there is another minus sign. So now let's take V of capital R on the right hand side and let's change this sign. So finally we obtain V of small r equal, so this minus sign and this minus sign cancel out, so we obtain rho divided by 3 epsilon naught times 2, let's go straight to 6 epsilon naught, okay, from here, times r square capital minus small r square, so this quantity here, the minus sign I already took care of it, the 6 I took care of it, minus V of capital R, but actually this minus, since I bring it on the other side, I change this minus sign, is also plus V of capital R, okay, from simple algebra. And once again, what is this quantity V of capital R? Well, this we already computed it earlier, and so we know that this quantity actually is equal to, as we computed a few minutes ago, rho divided by 3 epsilon naught capital R square. Okay, so now if you do some little algebra, so you plug in this quantity here, for example, you can multiply times 2 here, so that this one becomes a 6, and so here rho over 6 epsilon naught capital R square plus 2 times rho over 6 epsilon naught, of course, gives us 3 times rho over 6 epsilon naught. So, and in fact, let's keep it as such. We obtain finally that our V of small r is equal to, the function dependent of the square is minus rho divided by 6 epsilon naught minus rho over 6 epsilon naught small r square. Then this 1/6 constant plus 2/6 becomes 3/6, so plus 3 times rho divided by 6 epsilon naught, and I prefer to keep it as such because of the limits we're about to do. 6 and 6 is kind of easy to recompute things later. So 6 epsilon naught times capital R square, okay? So minus rho over 6 epsilon naught small r square plus 3 rho over 6 epsilon naught capital R square. So this is what we obtain in this case, and we can circle this quantity. Note that this is a common procedure. It is common to start from this region outside and move all the way to the region inside. Why is that? Because I can always do the limit for r that goes to plus infinite, and this allows me to find this kind of constants, okay? So it's useful to go from outside to inside, and this will happen again in the case of conductors. In fact, this is already the procedure you need to use to find the capacitance of a spherical capacitor, if you want. So that's very important. And remember, our capacitance is one of the aim which we want to find, for example, to explain a radio. Okay, so now we obtain this potential, and so this is the case for R in 0 to capital R. So now what we want to do next, we want to summarize this and plot it and find some limits. Okay, so to recap, our electrostatic potential V, which we found from E, looks as follows, mathematical form. V is only a function of small r, and is given by minus rho divided by 6 epsilon naught, not 63, times small r square plus 3 times rho divided by 6 epsilon naught capital R quantity square. And this is the electrostatic potential for small r in what region? In the region S0 to capital R, that is within the sphere, whereas outside is simply given by rho over 3 epsilon naught times capital R cube divided by a small r. So similar to this, but only divided by r. And this is in the region outside, that is from capital R included, in this case both included because it's continuous, all the way to plus infinity. It's a continuous function. Okay? As always, let's stress that it is a continuous function, capital R. Okay? In fact, let us perform as a sanity check formally the limit for small r that goes to capital R minus. Capital R minus, it means we are from this in this region, so we need to use this expression for v of r. So if we do that, we obtain by using the first expression, and this is r squared. So we obtain, that's why I kept the 6 epsilon naught in the denominator, because I get 3 rho minus rho, which is 2 rho, 2 over 6. 2 over 6 is 1/3. So I obtain rho divided by 3 epsilon naught times capital R squared. This hopefully should be the same, in fact it is, to the limit that goes to capital R plus of v of r. In this case we need to use the other expression, the one down here, because we're approaching from the plus side, okay, of things. And so if we're approaching from the plus side, we get r cubed over r, which is again exactly the same quantity, rho over 3x as expected, capital R squared. Okay, these two quantities are the same, which means v of r is a continuous function, a c naught, in the region from 0 to plus infinity, again as expected, because we know that the electrostatic potential has always to be continuous. Okay. Another thing we can compute, for example, is v at r equal 0. And if you just plug it in, of course, you need to use this expression here. So at r equals 0, this cancels out. And so we obtain 3 over 6, which is 1/2. So rho over 2 epsilon naught. Rho over 2 epsilon naught capital R squared, which is a quantity larger than this quantity here. And so if we were to plot, finally, if we were to plot, as in this case here, the electrostatic potential, there we plotted the field, here we plot the electrostatic potential V, and we want to plot it as a function of R, where this is the origin here. Well, we will find out that at this point, capital R, we will have a certain value. Okay, like that. This value happens to be rho divided by 3 epsilon naught all quantity times r squared, which is this quantity here. This is smaller than this quantity here. So this quantity here divided by 2 is the one up here at 0. And so in the first region, we have a dependence which is minus r squared. So it's a parabola inverted. So it looks like that. Continuously, we need to go as 1 over r to infinity. So it's continuous here. Here it goes as minus r squared, whereas here it goes as 1 over r. Colombian type outside. Inside is an inverted parabola with the minus sign. Is continuous at this point here, as expected from these two limits here. It has to be a continuous function. Here we have a point which is divided by 2, here divided by 3, so a little bit lower, and that's where it all gets connected together. So to recap this problem, we decided to find v from e, which typically you don't do, but it's a very interesting problem to learn how these integrals and these constants of integration work out. And so we started from the electrostatic field using this generic definition of E equal minus gradient of v, and setting up the integrals from the differential equation. The only thing we had to do is to choose two different regions and set different limits of integration. Starting from outside to inside, this allows us to use the zero condition at infinity to find v of capital R, which then we use also in the region inside to stitch up the potentials to be continuous according to these equations. We verified that the potential is continuous at capital R. We calculated also at 0. At infinity, of course, it goes to 0. Here is continuous at capital R, and it goes to this value over 2 here at the beginning. That's it.